be to talk about the particular science that is linked. There's a particular scientific discovery, result, project that is linked to these tutorials. So that is also part of understanding the context. And I think these two pieces would be useful to record, because if another student comes along and just takes the Python tutorial cold, they wouldn't have this context. So, and then we can go into the specific details. The third thing would be to actually go notebook by notebook and look at what each one is trying to do. It's designed to be mostly a self-driven activity. So it's fine for you guys to go ahead and do that in your own time later, but I think giving you this context would be helpful. Is that okay then?
Oh, sounds great. Sounds great. Okay. You can share your screen. I think you are familiar with Zoom.us. You can.
Yes.
You can,
yes.
Yeah.
No, I can share my screen easily if I need to. For now, I won't. Initially, I won't.
Okay.
Or actually, maybe I should. If it's okay with you,
yeah.
I will. I'll just show you a slide or two. And then when I bring up a paper, I'll show that. Is that okay?
Yeah.
Excuse me, guys, for interrupting. Raja, I'm not quite sure how many of the people installed Python and Anaconda on their machines. I'm wondering, shall you go through that steps?
Absolutely. That would be sort of the details of that. And those are described. It's described quite well in one of the Word documents.
Yeah, in the Word document. Yeah.
So I think that absolutely should be the place where people start, because you have to have Python running on your computer. Anaconda installation of Python would be useful. Then you can run a notebook.
Okay.
So I think we can talk about that. Let me say a little bit about sort of the philosophy of this thing. And I'm sorry if I'm going to be saying things you already know very well. So please give me a moment. And I just want to bring up one slide that I want to say a little bit about. Where is it? Okay. I assume you can still see me.
Yes.
Okay, and I will share my screen with you in just a minute. I want to just show a couple of. Let me do this. Let me take this over here. Sorry. All right, I will share my screen now, if that's okay.
Yes.
Do you see a screen with 4 boxes in it?
Yes, of different sizes. And it goes
yes,
in like
1, 2, 3, 4,
yes.
And different colors.
Yes.
So I just want to put this a little bit in context. Okay. So these 4 boxes represent 4 levels of engagement in STEM by a student. 4 levels. And a lot of the work I've come across that high school students do fall into one of these categories. And I'll just very quickly say about one, that it is a case where one is a passive activity where a student doesn't do the research, but they come into contact with the people and process behind it. People and process, both of those things. Very often if you read something in the media, you just see the result. You don't see the people, you don't see the process. But the people and process are important, and you can get this in many ways. You can get this by doing a project, but you can get this by watching Neil deGrasse Tyson's Cosmos video or David Attenborough's Life on Earth or things like that. Okay, so if you go to category 2, that is what we are talking about, learning Python. Okay, that's some of the skills to do research, and learning how to program is the most important skill today. But there are of course lab skills as well that are important. What we are going to be doing really falls into categories 2 and 3, because what we're going to do is in this Python tutorial, students are taken through a project, but I would call it controlled or pre-scripted, as opposed to open-ended. Open-ended would be the 4th category. Open-ended research is what most researchers do. You come up with a question, you don't know the way to the answer. You don't even know if there is an answer. You try to work on it and you fail many times. You learn from that failure. And ultimately, either you fail completely or you produce a result. Even if you fail completely, sometimes people write that up because other people will learn from that failure. So failure is embedded into that fabric. In a controlled research project, failure is not embedded. What I mean by a controlled research project is, let's take the case of this Python tutorial. It's based on a research project that my student, Claire Dorman, worked on a few years ago. This was part of her PhD thesis. It was the last paper from her PhD thesis. And when she wrote the paper up, it was a relatively convoluted path to get from the question to the answer. But once you've gone down that path, as long as you have a good memory and good documentation, even if the path is complicated, you know what that path is. And you can send another person down that path. Even an inexperienced person can go down that path. It's controlled. It's pre-scripted because you can script the path. The degree to which you prescribe it is the control you have. If you give the student a lot of direction, then it's easy for the student to go down the path. Even though the path was difficult for the researcher, it can be easy for the student because the researcher has already gone down the path. If I give the student very little instruction, then it can be quite difficult. So in this sense, it's controlled. The Python tutorial you have was developed by my student Claire Dorman and me, and with help from another later PhD student and another postdoc. So the four of us have really tried to design this tutorial. And what it is really a journey that Claire followed for that paper. And we'll talk about that paper in a minute. But it's a series of 6 Python Jupyter notebooks. And would it be helpful to say a few words about what a Jupyter notebook is? Or does everyone know what that is? What do you think? Are you guys familiar with a Jupyter notebook?
No.
I don't have it. No.
I've had a bit of experience.
I'm working. I'm familiar. I'm very familiar.
Okay. So, but let me say it for maybe Shaunak. Have you heard of it?
Yeah, I've heard of it. I think I've looked over it, but I don't really have that much exposure to it.
I won't take too much time. I'll just describe it very briefly. It's a browser interface for computer code, for Python code. That's all it is. It's a browser interface. Normally, you have a file containing the lines of instruction, computer code, and you can access that file through a text editor of many kinds. In this case, it's a browser-based interface for Python code. And the advantage of that is when you execute that code, suppose you execute a block of code, execute meaning you run it, then that block of code is supposed to do something. Suppose it's supposed to calculate a number. Well, it prints that number right out onto your browser. Okay, so the browser is both holds the code, but also displays the results of what that code is supposed to do. So if your code was designed to generate a plot, that plot shows up right below where the code is, always below where the block of code is. And it's a set of blocks of code. So if you literally hit Shift, Enter, and it runs that code. If the code was just supposed to load in some data and not generate anything, it'll come back silently. It won't put anything into the browser. If that load was supposed to print out something, it'll print it out right there on the browser. That's all a Jupyter notebook is. Is that, for those of you who have more experience than I do with a notebook, is that a reasonable description?
Oh, yes, very reasonable, yes.
Okay. So we took Claire Dorman's paper, which I'll show you in a minute, and we said, let's take the main analysis steps and compile them. Claire was already working in notebooks. Let's compile them. Let's polish it up, because if you're using it yourself versus somebody else using it, you need to tidy it up. So we have 4 notebooks that carry out 4 steps in the analysis process of going from a question to an answer. But you have 6 notebooks. The first 2 are introductory Python commands. So they have nothing to do with Claire's scientific paper. It's just a series of commands. The second notebook in particular is a very long list of Python commands. How do you make a plot? How do you do this calculation. I treat that as a reference thing. You can do the same, but really your best reference is the Google bar. You can search it, you can type Python, and you can type in some command. You say, how do I take a square root? If you just type in square root Python, it will tell you exactly what to do. So I feel that references like that notebook are of limited value. Your search engine is much more useful. So the first two notebooks are just Python commands. The next four are really the meat of this controlled research project. It's like I say, it's a controlled research project because you'll see, I'll tell you in a minute how we are controlling it, but you're also learning the scale of Python. So it's really it straddles those two categories, the activity you're doing. Now, what we've done with the code, a notebook, like I say, is just lines of code. What we've done with the code is, it's arranged into blocks. We've kept most of the blocks intact. So you can hit Shift Enter and you can see what it's doing. It'll make a plot. It'll read in some data. As we get deeper into each notebook, and as you go from notebook 1 to 2 to 3 to 4, they get a little harder and harder. What we do is we take sentences, we take lines of code, and we replace them with English sentences with a comment in front. We put a hash mark in front, so the interpreter is not trying to run that line of code. If it sees a hash mark, it says, if it's got a hashtag there, it says, this is a line of English that we want the user to see. It's not code. But what we've done is we've replaced actual code with sentences. And we are saying to the student who's learning Python, do the opposite translation, turn that English sentence back into a line of Python. And the guidance you have to do that is your first few blocks are already working. They have not been changed. So you can see what they're doing. You can see the plots they make. Effectively, when you see a plot, and if you describe a plot that one of the early blocks makes, you're really translating Python into English. You're saying, okay, this line of code made the points red. This line of code labeled the axis. This line of code did put a boundary. Things like that. So you already, by looking at a plot, you can already translate Python into English, and then we ask you to do the reverse translation as you get deeper into the notebook. That's the philosophy behind it. Okay. Simple as that. What you get for free is a journey through a real science paper. I say real, it was real in 2015 when it was published. Now it's no longer at the cutting edge of research. Just because once something is published, it's no longer at the cutting edge. Someone repeating that exercise can't publish it because it's already been published. In that sense, it's away from the cutting edge. The question is still of great interest, and we're applying these techniques to other galaxies, etc. So, any questions at this point? Because this sort of gives you an overview of what the 6 Python notebooks are. Like I said, the last 4 are really where you have to do this reverse translation. The first 2 work just fine. Any questions at this point?
So far, so good.
Okay, all right, good. So one other thing I was going to say about the notebooks. Okay, no, let's plunge in and let's take a quick look at Claire's paper. So we can walk through what the basic science question is and what the result is. I'm giving away the answer. I'm giving you what result you're going to find at the end, because that's not the goal of this. The goal is not to find the answer. The goal is to understand the process in this case. Understand the tools and the process. Oh yes, what I was going to say is this is certainly not a comprehensive Python tutorial. There are many, many, many more commands in Python than are contained in these 4 notebooks. It'll only give you a basic introduction to Python, a very limited introduction. I just want to say that. After all, it's being taught by somebody who hardly knows Python at all, me. So it's very rudimentary in terms of the level of difficulty. My students are running circles around me in terms of Python coding all the time. Why Python? Any kind of coding. So I'm learning little bits from them. As you can see, I'm learning from Emily and Claire what this coding is. Okay, so I'm gonna get out of this screen and close this up, and for a moment show you Claire Dorman's paper. Bring that up here. Let's see, where is it? I was starting to write an email to yourself, but now, let's see. Can you still see my screen?
Yes, we have a screen with a bunch of papers.
A bunch of papers.
The
Okay,
ADS. Good. You have the ADS showing.
Yeah, I have ADS over here. And the student's name is Claire Dorman. You can see one of her papers here. That's not the one I want. I want a different paper. I want this paper. Clear age velocity dispersion correlation in Andromeda stellar disk. I'm just bringing up the PDF file. And again, I won't bore you with the details, but I'm happy to, I don't know if I made this paper available already to the students, but let me send you a link to this paper through Zoom. Okay.
Okay.
Let's see. I'm looking to send you chat. There we go.
Excuse me, Raja, would you mind also sending an email to us with the paper, because when we go out of Zoom, we may lose the link.
I don't have everybody's email, but I'll send
You can send it to me, and I can forward to everyone. No problem.
Perfect. Thank you. Sorry for the interruption.
I have Ognian and Rick on here. I don't have Shaunak and I don't have.
Yeah, don't worry. Perfect. That will work.
Okay, good.
Yeah.
It's a very impersonal email. It just has a link.
There you go.
I'll go back to looking at the paper very quickly. So a few things about it. It's based on images taken with the Hubble Space Telescope and spectra taken with the Keck telescope. Okay. So remember, notebooks 1 and 2 are really not related to this science paper. So let's ignore them for now. Notebook 3 is related to Hubble Space Telescope data.
Mm-hmm.
Notebooks 4, 5, and 6 are based on, actually notebooks 4 and 6 are based on Keck data. So spectra taken with the Keck telescope. And you're probably wondering about notebook 5. Well, it's a computer model of Andromeda. Okay. So again, notebook 3 is Hubble data. Notebooks 4 and 6 are Keck data, Keck spectra. Hubble is images, Keck spectra. And notebook 5 is a computer model of Andromeda's disk. So I'm just going to scroll down this paper, and I'll just pause at a few images and few plots just to present the basics. You see an image of Andromeda there, can you?
Mm-hmm.
I'll zoom in a little bit.
Yes.
Can you guys see this image? Is that better?
Yeah. You can see.
Okay, so that's an ultraviolet image of Andromeda, and you can see its disk. So you can see the center as the bright spot, but the white rectangle and pink rectangles are the regions studied by Hubble and Keck, respectively. Where it says FAT, P-H-A-T in white, that's Hubble. And the H in FAT stands for Hubble. And SPLASH is a different acronym, but those were taken with Keck. All the pink was taken with Keck. And this notebook is really based on the overlap of those two surveys. So if you see a pink area with no white rectangle, that's not part of this. Or if you see a white area with no pink under it, that's also not part of this. It's really based on the overlap. Okay. So I'll zoom out again a little bit and navigate. I hope this is useful. I hope I'm not wasting your time. What do you guys think?
That is great, because you're telling us where are you getting the data from, what kind of notebooks how you're using the notebooks. We are getting an idea. So at least, I mean, from software point of view, which libraries are used and how they're used. So that's useful.
I'm going to go on then, because I'm going in what I consider to be a logical order. But okay, so I'm going next to Figure 6. And what I'm showing you here is two panels, right? You can see two panels. And the x-axis is a measure of the color or temperature of a star. Mm-hmm. They're synonymous with each other. A color of a star is an indication of its temperature. The y-axis is a measure of its brightness, how bright it is. Bright stars are at the top, faint stars are at the bottom. It's a magnitude as measured in infrared light. F814W, it says, on the y-axis. Yeah. 814 is the wavelength in nanometers of the light of the filter that's used to measure the brightness of the star. So we only let in light of that color, near infrared light. 814 nanometers is beyond what the eye can see. And we measure how bright the star is. Again, that's the y-axis. Bright stars at the top, faint stars at the bottom. And on the left, you see the full Hubble color magnitude diagram. These are called color magnitude diagrams. Now, are you all familiar with Hertzsprung-Russell diagram? This is especially a question for the two students, Shaunak and Philip.
Yeah.
This is a Hertzsprung-Russell diagram. Temperature running from right to left, not left to right, right to left, and brightness running from bottom to top, getting brighter as you go up. It's a little bit scary how much data Hubble can collect, because you can see that every dot is a star. That's what you're seeing in the right panel.
From calendar.
Those are only the
Celso's faculty evaluation.
Hello? Audio. Hello?
I'm sorry, I had some background noise here.
Oh, no problem. No problem. That's okay. Okay. So I'm looking at I just want to say that with Hubble was able to measure brightnesses for 117 million stars in Andromeda. 117 million. Of those, we got spectra for a subset, about 6,000 stars, that are shown in the boxes in the left panel. And those boxes appear again in the right panel. So the Python notebook is really based on these 6,000 stars. It's really, I think 5850 is the number of stars used. Okay.
Excuse me, one question here. How fast is the notebook? Because most of the processes are running in the browser and you're loading the data for 6,000 stars. Is it processing it for some time, or is it processing it right away?
Right away, because 6,000 is still a small number and you have very limited information. We've only given, for this notebook, the data file we made available is only what you need for the notebook, not the full data set we have.
Okay, thank you.
It's quick. It's quite quick. Yeah, it should. Now, so basically, we grouped, based on their color and brightness, you can group stars into, in this case, 4 categories, not 5, 4 categories. This region where my cursor is sort of a blended region where different kinds of stars land, so we're ignoring that region. On the left, you have stars that are very short-lived. On the upper right, you have stars that live for a little bit longer. In the middle right, you have stars that live for even longer. And then these are the longest lived stars, called RGB. Red giant stars live for 10 billion years. Older AGB stars live for maybe 2 or 3, maybe 5 billion years. Younger AGB live for maybe 1 or 2 billion years. And main sequence stars, the ones over here, live for much less than 1 billion years. 100 million years, 50 million years. Okay. So these are 4 populations of stars that you can use the Hubble data to identify and classify. You can group your stars into 4 categories that live for different lengths of time. Okay. That's what you'll see as the end of the first notebook. In the first notebook, you'll be grouping stars into, just to make it easier, we ask you to group it into 3 groups, not 4. Older AGB and younger AGB will be lumped into 1 category. The RGB, red giant branch, will be one category. AGB, by the way, stands for asymptotic giant branch. And MS stands for main sequence. That will be the third category. So in your notebook, you'll be grouping stars into not 4, but 3 categories. And that's really the end of the first notebook. You'll be making a plot, and you'll be writing out these data files, 4 separate data files, 3 separate data files, 1 for each of the categories. Does that make sense? Okay. Can I go on to the second notebook?
Yeah.
Okay. So in the second notebook, it's based on Keck data. What you do is you take spectra that we've already provided you. We provide you 4 spectra only, not too many, just 4 spectra. And what I'm showing you here are examples, actual spectra of individual stars in the Andromeda Galaxy taken with the Keck telescope. And the y-axis is a measure of brightness, but it's a brightness of the star at a particular wavelength. That is, the light of a star is emitted in many different wavelengths. And a spectrum is really taking the light of a star and taking the energy from a star and plotting it as a function of wavelength. That's all a spectrum is. You can see wavelength is on the x-axis in angstroms. An angstrom is 1/10 of a nanometer. And you've got wavelength running. And again, remember, we saw 814. So that would be 8140 angstroms. 814 nanometers is 8140 angstroms. That would be in this part of the spectrum that I've got my cursor on. Okay. So you've got different kinds of stars whose spectra you can see on the top panel. SG stands for supergiant. AGB is asymptotic giant branch. You have 2 different kinds of AGB stars, cooler and, redder is cooler. The upper one is hotter, and then an RGB star. And if you zoom in on these spectra, you'll see that the spectra are not flat. They have all kinds of wiggles in them. There are dips in them, typically. Dips, steps. And what you're seeing is in each of these panels, I believe the gray or colored line, it should say over here in the bottom panel, what does it say? It's been a zoom in view of portions of the spectrum for obtaining velocity. The science spectra are color coded, whereas there are some templates shown in gray. I don't know if you can see a gray line also. For each star, there's a gray line. A gray line is a spectrum of a star that we know a lot of information about. There are many stars like the sun that we have a lot of information about. We know how fast it's moving. So if we take a spectrum of such a star, typically it's a bright star, we know exactly how fast it's moving. We take its spectrum and then we shift the spectrum so that we mimic what the spectrum would look like if that star were not moving. So we create these templates of what stellar spectra should look like if the star is not moving at all. Then, in that second notebook, you get to set up a Doppler shift formula, and you take a spectrum and you ask how much must I shift these templates so that they match the science star. You basically can measure the velocity of a star from the shift in its spectrum. And Shaunak, you had to do something like this for your project last year.
Yeah.
So this is not using emission lines of galaxies, but using absorption lines of stars. That's what you have to do in the second notebook, is by eye, you have to find the velocity of 4 stars. To find the velocity of a star, you first take its spectrum, and then you look for another spectrum in your library of templates. We give you 4 templates or 3 templates. In reality, we have 30 templates. So in reality, what we have to do is find the template that looks most like our science star, and then ask how much Doppler shift must be applied till they match. We don't do this by eye. We ask you to do this by eye in your Python notebook. In reality, we use cross-correlation techniques. Similar techniques that Google uses to find words, to search for documents, things like that. It's a pattern matching technique. We're looking to match one pattern against another pattern. So that's what you'll do in the second notebook, is learn how Doppler shift works and how to measure velocities from spectra. That's why I say it's based on spectra, based on the Keck telescope. Okay, can I move on to the third notebook?
Yeah.
Actually, before I leave the second notebook, at the very end of the second notebook, we ask you to make a map. And that map is a map of velocity of the star as measured through your Doppler shift as a function of its position in the sky. I'm going to show you a diagram here in Claire's paper. Okay, so if you look at the diagram in the lower right, the one that I'm zooming in on now, so you should be able to see two panels, and I'm going to focus on the one on the right. The X marks the center of the galaxy, of the Andromeda galaxy. And what you're seeing here is a portion of an ellipse. Okay, imagine an ellipse, an oval that is, whose symmetry center is that X. So like I say, you're seeing a portion of the ellipse. You're only seeing the upper left part of the ellipse. You're not seeing the whole ellipse. It's a tilted ellipse, mind you. It's a tilted ellipse, and the ellipse, if you can see my cursor, it goes around like that, but you're only seeing the upper left part of the ellipse. Does that make sense? So Andromeda, of course, is shaped like an ellipse, or looks like it's shaped like an ellipse from our perspective, because it's actually shaped like a circle. It's shaped like a plane, a circular plane, but since that plane is oriented at some angle, it looks like an ellipse from our perspective. Okay? But it's a rotating plane. It's rotating such that the upper part of Andromeda is moving away from us. The lower part of the ellipse is coming towards us. It's a rotating ellipse. Does that make sense? Yeah?
Yeah.
Yes.
Okay. So the center of Andromeda is also moving. It's not stationary relative to us. The center of Andromeda is coming towards us. We're going to be in a collision with Andromeda in a few billion years. So the center of Andromeda has a negative velocity. Velocities are said to be negative if the thing is approaching you, because dr dt is negative, r is decreasing as t goes forward. So the signs of dr and dt are opposite from each other if you've done calculus for the two students. So velocity is dr dt, and it's negative if r is decreasing as t increases. So Andromeda has a negative velocity, but it's rotating. So the upper left part has a less negative velocity than the central part. Okay. So in this map, every dot is a star, but they're not color-coded by velocity. If they were, you'd see a very systematic pattern. And that is really what you'll come to at the end of Notebook 2. You'll come to a velocity map. Okay. In Notebook 3, I don't have a good analog of it in Claire's paper, but in Notebook 3, what will happen is you'll get to make a map like this, a fake map out of a fake galaxy, and there the whole ellipse will be filled in, because this ellipse is partly and Keck, we could not cover all of the Andromeda galaxy. But a computer program is cheap. It can mimic, or you'll make, sorry, not Notebook 3. This is Notebook 5 we're talking about. I'm sorry, I gave you wrong notebook numbers. The very first notebook number where you separate stars into different long-lived, short-lived, that's Notebook 3. The notebook where you measure velocities and make a velocity map, that's Notebook 4. Notebook 5 is where you use to make a model of Andromeda, and you tweak the parameters. How tilted is Andromeda's disk? How fast is Andromeda rotating? You tilt it to mimic the map you made at the end of Notebook 4. And in Notebook 5, you study how regular is the rotation of Andromeda's disk for very short-lived stars and for very long-lived stars. And that brings us sort of to the final result in Claire's paper, which is she found, I'm going to come to the paper in a minute, sorry, this plot over here, she found that the shortest lived stars, which are in blue, have what is called a very low velocity dispersion, and the longest lived stars, the red stars, have a large velocity dispersion. Velocity dispersion is a measure of how well behaved the stars are. If the stars are all moving coherently all together, that's a low dispersion. So the shortest lived stars are well behaved. the longest lived stars are poorly behaved. They're not very disciplined. The different stars are not, each star is, they're very independent. Each star is following its own path. They're not following the other stars. Whereas the blue stars in blue, the main sequence stars, short-lived stars, have a herd mentality. Every star is following the others. So it's a sort of herd mentality. So blue star are like cattle, red star are like people. People are independent. People are not all moving together. Or a better analogy would be a blue star is a marching band where a group of people are, a group of students are marching around a circular field. They're all marching together. They've trained for a long time. So they're all marching together. The red group is like a marching band that hasn't had much practice. So different people are going at different speeds. They're going in sometimes even in different directions. So they're a very indisciplined marching band. And what we find in Andromeda is we see this trend. This plot that you're seeing is the trend that became the focal point of Claire's paper. We found that very short-lived stars have very beautifully coherent motion. Long-lived stars have incoherent motion, and that's because Andromeda, over its lifetime, has been bombarded by other galaxies, and they tend to knock stars out of their original orbit. When stars are born, they're born in a very disciplined way. Short-lived stars, like the blue ones, live for such a short time that they haven't had the occasion to be bombarded by too many things. Long-lived stars, like the ones in red, have been bombarded many times, and so they have chaotic kinematics.
Out of curiosity, do you observe the same type of behavior in our galaxy?
What you see in our own galaxy is marked with the orange and magenta points.
Oh.
So yes, we see a trend, but the trend is much shallower, and our galaxy is not as chaotic overall. That is, there's a 0-point slope difference. MW stands for Milky Way.
Oh, okay.
Now, it's a little bit of an apples and oranges comparison. In our Milky Way, we can only see the stars that are very close to us. In Andromeda, we can see a large part of the galaxy at once. So it's a little tricky to compare one to the other, but just on the face of this evidence, if our neighborhood of the Milky Way, this is ironical. In our own galaxy, we can only see our own neighborhood. In Andromeda, we can see the whole thing. So our own neighborhood is I think the most direct statement we can say is our own neighborhood of the Milky Way is less disturbed than Andromeda. Both that is the 0 point of this dispersion is smaller, and that the rate at which things have been stirred up is also smaller in the Milky Way. But this really applies to our neighborhood in the Milky Way. So that's why I say it's a bit of an apples to oranges comparison. It's a very good question, Celso. That's it. That's what I have. And we have 10 minutes left, so I'm hoping we can talk about questions. I'll stop sharing my screen if that's okay, or or we can talk about anything else. So I will stop sharing, and let's spend this time just reflecting on questions you have. Anything interesting you saw, or any other things you want to talk about? Absolutely.
I'm going back to look at coding, and again, I'm not in Python. I'm in IDL. Now there is a workbench, which I think is similar to what you were mentioning with Notebook. I wonder if you could show the coding of one of these plots, how one of these plots is generated, if that is possible, just to have an idea.
Let me see if I can bring that up. I may not be able to do it as easily as I thought. Let me see.
And now I'm noticing Ognian is in the dark now. the night got him.
Let me
I wish I had a notebook open. I don't have anything open. I have it on Give me a moment. Let me try to bring it up. Just give me 1 minute.
It's just more for the students, just to give it.
Absolutely. No, I think it's a good question. It's a very good question. Let me plug in my USB. I have my code on an external drive for a moment, and nothing on this particular laptop. So I've just plugged it in. Give me one moment. I'll try to bring it up. If I manage to bring it up, what I will do is share my screen again.
Okay, sounds good.
And if I don't manage to bring it up, I just rebooted my computer. Unfortunately, I'm going through a little bit of a transition with my computer, so that's why I don't have it handy. But let me see if I can find it. In the meantime, please ask any questions you have, because it's really, this is your session.
I have several questions.
Please go for it.
Yeah. First, for the availability of the data, I was experimenting with ESO data. ESO data is available freely and online. How is with data from Keck and Hubble? Is there historical data available, or it is limited for scientists?
Oh, Hubble has the best archive in the whole world. It has all kinds of historical data. Hubble does. Keck has some, but Keck is mostly a spectroscopic telescope. So unless you know what the experiment was, it's very hard to make sense of it. Hubble has lots of data. I mean, Shonak used Keck data for his project, but we had to, whenever you take a spectrum, you have to know how bright it is, where it is, whereas with an image, things are quite a bit easier. Okay, so I am actually going to share my screen because I have something up that I can show you. Is that okay?
Yeah.
Okay, so let me just quickly go back to my screen. And you should see a terminal window where, do you see that?
Yes, that Xterm, yes.
Okay, so I've already installed Anaconda Python, and so I've got an Xterm with a bunch of code in it, but I can type this from any terminal. I'm typing Jupyter Notebook. Okay, and when I do that, it will open up, it'll give me some messages. It's starting up a kernel, but you notice it's opened up a Firefox browser.
Oh, interesting.
Okay, I automatically opened it up, right? And I started this in a directory where I already had some Jupyter notebooks. Jupyter used to be called IPython. That's why IPyNB is IPython notebook. And let me open up this one. So I click on this, and when I click on it, it opens it up in a new tab. And when I said there are blocks of code and there are things that it can read in and can make plots, that's exactly what what it's bringing up. It's taking a little bit of time because this is not your notebook. This is a different one. This is an actual project that I'm working on right now. But you can see that, and it's, the comments are written by high school students, so it says the less yucky working code. And technically, this first block, if I want to execute it, it's not going to do anything. It's just comment. I can execute it in two ways. I can hit the this button, which says run the cell, or I can, even easier, I can go in here and I can hit Shift Enter. When I do that, you notice how the highlighting has shifted to the next panel. Do you see that? It's now saying in 1. So now if I hit Shift Enter, or let me this time run it this way, you see it's run it. It was that quick because it's just initializing things. And these are some import statements, and you'll see something like in the notebook, right? You'll see this. Right. Then I'll hit Shift Enter again. It's gone to the next one. This is a time-consuming step. If I were to run this, it would take a while. I will run it, and while it's running, you'll notice that, it ran quite quickly. Okay, it ran quickly. I'm going to load this. Sorry about that. So this part is the time-consuming step. It is taking some time to read in the data. And you notice that the previous ones, the number immediately came back, but here you notice that there's an asterisk where my cursor is. That means it's still running. When it's finished, that asterisk will turn into a number. The other way you know it's still running is you see at the top it says busy.
Okay.
Do you see that? Where my cursor is at the top on the tab? Can you guys see that?
Yeah.
Yes.
Yes.
So that means it's taking a while to run because it's a very big data set. This time it's reading in my full database from the Andromeda survey. There's 25,000 stars, not just the 5,000 I gave you, plus it's got all kinds of information. It's got spectra for everything. Whereas that's not what's used in the Jupyter in the Python tutorial. We just give you a limited amount of data there. Otherwise, it would take very long.
Excuse me, Raja. Very short question. For visualization, you're using the matplot library, right?
Yes, matplotlib. Yes, exactly. You see that over here. I'm going to highlight it here. You can see that here.
Okay, cool.
And we have set up something called NumPy, which is sort of which you use a lot. Everyone, AstroPy that you were talking about. But you can see that these libraries have directory structures. Like AstroPy, there's astropy.io for input-output. So these libraries have a directory structure to them. So you could have astropy.io. Within that, there is something called fits. So you import fits. I could have written over here, import fits as F, in which case I'm creating a shortcut. I don't have to call it fits. I can just call it F. But I'm not going to do that because it will mess. So if I had said as F, then over here, I wouldn't have said fits.open. I would say f.open. Does that make sense?
Yeah.
Because the open is a built-in Python command that's within the fits library, which is under IO, which is under AstroPy. So I'm importing only the fits reader and writer from astropy.io, and I'm calling that fits, or that's its default name, but I could have changed its name to something else. Mm-hmm. And you can see that I used fits.open in that third block. And this path name that you see here, this path name variable is actually read in one of these things. So you'll see a lot of Unix. It's still running. This thing takes a few minutes to read in the data, sorry. But, these are the blocks we were talking about. These blocks won't work because till it reads in the data, it can't generate these. But I think I have possibly I have, this is a very long piece of code. But, you can make plots like these. Here you go. There are plots over here. And I can't remake these plots right now because the stuff is still running. But the reading in the data is still running, but there's a plot. Oops, sorry. There is a plot.
So I'm sorry. These plots are they generated inside the code, so you can visualize as it goes?
Yes, this plot that you're seeing here, Celso, this very plot is generated by the block of code that's right above it.
Wow.
It's using a command called py.plot. That's the command. WV stands for wavelength. That's the x coordinate. And the next thing, ctemp spec, which is this quantity, that's the y coordinate. Color equals B is color is blue. And you can see that it's plotted not one, but 4 different spectra in 4 different colors, blue, green, red, and orange. Orange is this line.
And you already cross-correlated then because they are all nicely shifted to the same wavelength.
Yeah, all of these spectra in the rest frame. That's why they're already matching. But in this program, we're not trying to measure Doppler shifts. We're trying to measure what kind of star. So this is doing something slightly different. And you can also see that there is a print command in here at the end. It says print something here, scale factor, print slope. And so that's what it's printed out. The slope command, we haven't yet, this line that you see highlighted was added after we ran the code the last time. So what you're seeing here is the results of the last running of the code, but any changes we've made to this block, you're not seeing the results of that below. Okay. And I can't quite run it yet because it's still reading in the data.
Yes.
But where is the data? Now it's read it in. It's finished. So I think it finished this step, right? I think that's what was...
now we have a number 4 in there.
Sorry?
Now you have the number 4 instead.
Exactly. So, and I can go through these very quickly. I'm running them. You can see they're running. And it's very quick. I'm going to run this one. These error messages that you get are, standard things, nothing to worry about. I know that because I run it now many times. And then it's running through these pieces of code. I'm just hitting shift and enter. When as soon as it finishes one, it goes to the next one. Now, if I were to run this block, it would take a little bit of time. But even without, so blocks 18, 19, and especially this block over here, all other stars, takes a very long time. So I don't want to run them. Instead, I want to run this block. I don't know if it will let me run that. No, it's giving me an error because it has a dependency on an earlier block that I haven't yet created.
You have to run the long running block. Yeah, that's.
Sorry, I have to run
You have to run the long running the block which is taking a lot of time. Yeah, that's linear. Yeah.
That's right. So I think if I run the block that I'm running now, if I run it, it will take several minutes. But if I finish that block, then I'll be able to run the block that just gave me an error message. But you'll see that this block, I'll just show you a little bit of code over here if you want. This is a block that's running right now, the one that's highlighted. And notice it says if counter %10 equals 0, print string counter plus done. So what that means is it's going through a list of stars, and you notice how it just says 10 done. Did you see that appear?
Mm-hmm. 10 done, yeah.
Yeah. So what that's saying is it's finished 10 stars. And what it's saying is if the counter, the % sign is like taking a modulus. So if 15 modulus 10 is not going to be 0, 15 modulus 10 is going to be 5. 12 modulus 10 is going to be 2. So only when the modulus is 0, it prints it out. So it prints it out for the 10th star, the 20th star. It's a way of keeping track of progress without printing out each one. Does that make sense?
Yeah.
So it says 10 done, 20 done. By the way, it's past 8 o'clock. So if you guys need to go, we can end it because I think we've covered quite a lot actually.
No, we have 30 there. I have another question. So you work in a group, you have your students. How is this code divided? So everybody has access to it, or you have just one student working on it?
That's a very good question. That's a very, very good question, Sal. So far, I'm working with one student, and for this particular project that you're looking at, working with one student, we trade notebooks. She makes some changes, she sends it to me, or I make some changes, I send it back to her. In the past, we've used GitHub, and just to do version control so that people can check out the code, they can make modifications, they can put it back in.
So you said you are using it in the past. What was inconvenient with GitHub? Just out of curiosity.
No, nothing was inconvenient. No. It's just that right now I'm working with one person on this notebook.
Okay.
And so we're not using GitHub for it, and she's doing most of the coding. So it's really one person working on it. Otherwise, yeah. Using GitHub.
Because with GitHub, you can also trade notebooks there too.
Yes, you could trade notebooks. That's what we were doing. We were trading notebooks there, but we were using something called Bitbucket.
Okay.
Oh, I'm sorry. I forgot to introduce Lee Rottler.
Hey Lee, how are you? Old friend.
How are you, Raja?
Good. Where are you? Oh, there you are, Lee. Okay.
Can you see me? I don't know if my camera's working. Oh yeah, it's working.
No, I can see you. You can't see me because I'm sharing my screen. But the carbon stars are nearly done. There's 70, finished 70, and I think it has a total of 99 to work on. So if this is finished, as soon as this finishes, I can show you something else. But I've already cut 5 minutes gone 5 minutes beyond 8 o'clock. So do you guys need to leave?
No problem. Go for it.
I'm pretty much there. I don't know if there's anything else. I can just show you that one block of code that's generating a plot, just to give you a specific sense of what it does. Let me just give me 1 minute, and I'll. It's 80 done. After it's done 99, this block will be finished, and we won't have to run the block below it. That takes many hours to run, but we'll go straight to the plotting section. Almost there. 80 done. It'll do 90 done, and then it'll highlight the next block. And it's still got a star over here. As soon as this turns into a number, it will be done. I'm surprised it doesn't say busy at the top here, but I don't know.
Yeah, it's still with a star in there.
Sorry?
You still have a star in there. So
Yeah,
it's still working.
normally I would expect it to say busy up here
Yeah.
in the tab. Okay, there we go. Now it's done.
Yeah.
Okay, so now I'm just going to quickly go down to the block we were looking at before, this block, and try to generate the plot. Yeah, see, it generates the plot. So, for example, if I wanted to do something very simple, you can see the numbers here are 1.0.5, 1.0. Okay, so you can see these numbers are, this one big tick mark is half. So if I just took the blue one and I added plus 0.5 to it, what do you think this will do?
We'll shift it up.
It'll shift it up. So if I just do this and hit Shift Enter, that's all I'm doing. You can see what it's done.
It generates again and then shifted. That's amazing.
Yeah. It's very convenient. It's a very convenient way to learn. And I didn't have to compile, nothing. I just hit Shift Enter.
So you don't need to read the stars again. You don't need to calculate everything again.
Right. And so if I take the wavelength and if I multiply it by 1 plus V over C, okay?
Then you have
If I do that, and I have to define what C is. C is equal to 300,000. And let's choose a velocity. Minus 300, which is the velocity of Andromeda. If I do this, it will do a different kind of shift. You notice how now the blue star is not lined up? You notice these dips are not lined up. Before it was beautifully lined up. If I change the velocity to 0, it will line up beautifully again. So I've shifted by 40 kilometers per second, the blue star relative to the others. And I don't know if you can see, but the blue stars is definitely shifted to the right.
Yeah.
So that gives you an idea of how sensitive it is, right?
Yeah.
10, we won't be able to tell.
Yeah, we can tell.
So 10 is hard to see.
Yeah.
But 40, we could tell. And if I just put 0, then of course, by definition, it is lined up. We know it's lined up. So you can see very simple changes to the code you can implement here. I'm going to just undo all this stuff because I don't want to mess up something that is working. You can change colors, you can change the boldness of the line, you can do all kinds of things. So this is an example of a plot. If you just do pi.plot, it connects an ordered set of numbers, x and y. If I did pi.scatter, it will produce something very different.
You give you the points.
It produces a set of dots that are not connected.
Yeah.
Okay. Can you guys see that?
Yep.
So I'll change it back. So for a spectrum, obviously pi.plot works better. But if you wanted to look at a distribution of points and you don't have an ordered set, a scatter diagram is just fine.
Well, one thing that people might be interested in is that the matplotlib webpage, I forget the exact webpage now, but it has a list of examples. So if there's some plotting that you need to do that is different from this or more sophisticated, you can go. They have almost every example you'd want there on the line, and you can copy and paste the code.
Yeah, and the second notebook in the set has many examples of different kinds of plot also.
Yeah.
In this Python tutorial set, the second one is just a series of different kinds of commands for different kinds of plots. So I use pi.scatter, I use pi.plot. You can use pi.hist to make a histogram.
Yeah. Yeah, it's really powerful.
Very powerful. Very, very.
I think they should have at least 60 to 90 examples with any kind of complexity, business, science, and so on and so on. My matplotlib is very, very, very powerful.
Yes.
Yeah.
All I have. That's really all I have. I mean, we can, I think it would be useful. I'm happy to get on another call after you guys have played with the notebooks.
That's excellent. That's very excellent. For me, it was an awakening after 20 years without saying this. It's amazing that you can kind of go dive inside the code and see results as they are being produced. It's amazing.
No, but this interface I find so beautiful.
Yeah.
I mean, I program in much uglier environments than this. This is so nice.
Yeah,
Well,
it's
same
like,
here.
as you said, you have a browser, you have your code, you have plots, have everything in there.
Yeah.
It's amazing.
I thought it was great when IPython came out, but Jupyter, that it beats everything.
Very
I've been programming with Jupyter for a long time, but that's the nice thing is you can do things very quickly. What would normally take a week, you could do it in like 2 hours with Jupyter.
Really, it is very versatile, I have to say.
Yeah.
And it is very forgiving. Something what with Java you will need to have an IDE and to be very careful. Python just works.
Oh yeah, I hate Java. Another thing too, what I like about Jupyter, can everyone hear me?
Yes.
Yes.
I can hear you.
The nice thing about Jupyter is that if you have to use other languages, you can by just changing the kernel. What Raja was using was the Python kernel. In fact, Python, was it 3.6 that you were using, Raja, or 3.5 or
3.6 is what we
3.6? Yeah, and you can also use. There's a new language that's been out for about 3 to 4 years. It's called Julia. So if you have compute intensive functions, functions that require a lot of CPU cycles, and take a long time. Basically mathematical functions that you have to compute all the time. It can be as fast if you write it properly. It can be almost as fast as C and Fortran, but it's as easy to program in Julia as it is Python. It's very Python-like, but the nice thing is Jupyter has a kernel for Julia as well. So having Jupyter is just fantastic because you can use it not just for Python but for many other languages as well. Right. So I like to use a combination of Python and Julia, where Julia I use for for any type of modeling that requires a lot of computation.
I was also going to say that you can have Python in standalone outside Jupyter, but you can easily go back and forth between notebooks and standalone Python code.
For me, the major advantage of Jupyter is because you put the explanation, the comments, in the in HTML formats, and then you have the box for the code, and it fits very well together. The comments for the software with the source code. While if you use an IDE, some kind of regular IDE, then the comments are somehow, between the lines.
Yes.
Basically, Jupyter can be used for, it's great for tutorials, or if you want to write a book and mix code with your book.
That is the power of Jupyter. That's why it is widely adopted, not only by astronomical community, also by machine learning community. It's widely adopted.
That's right. Yeah. And for the astronomy community, it also interfaces well with something called LaTeX, which is create a figure, you can create a caption right there.
Mm-hmm. Yeah. Yeah, it's beautiful.
All right. So I would like to thank you, Raja.
You're most welcome.
And it's being taped, and Pranati Murundi, she texted me saying that she couldn't get into Zoom and she want to see the taped version of this talk, and so we will pass it along, and maybe later in the second semester, depending on where we are, would be nice if you could have some time and visit us again. That would be great.
Absolutely.
Yep.
So Raja, did you put a link to the GitHub where this is all stored?
No, I actually didn't put a link to GitHub. I just have the notebooks and instructions for Python in a simple website that I sent also.
Okay. It's okay if we download and steal from it, right?
Of course.
That's what I do.
It's a bunch of pirates. That's what we are.
No, it's absolutely. It's Claire, Emily, Kyle's, and mine, but for education. So the data, that's why we didn't release all of the data. We released only part of the data that we need for this.
Yeah. Absolutely. Okay, great. Thanks, Raja. I really appreciate it.
All right. Thank you.
Awesome. Thank you.
Thank you.
Yeah,
thank
thank
you
you, Raja.
very much.
Thank you.
And
Thanks a lot. Nice seeing you again.
Okay, good seeing you. Bye.
Bye.
Bye bye.
bye-bye.
Bye, guys.